is the solution, and then I'm going to give you the second result where the function is an odd function. Is it okay? Can I erase it? Hello, guys. Can I erase it?
Yes, sir.
All right. Thank you. Now, for an odd function, it's going to be easier. The integral going to be automatically equal to 0. So it means at the beginning, when you realize you guys have an odd function, to integrate from negative a to a, you can just mention since you have an odd function, so the integral going to be 0. But be careful. I'm not saying, you know, for all interval. I said if you integrate from a number to its opposite. Okay. I'm going to give you an example. Let's say you integrate, let's say from -2 to 2, and your odd function is x cubed, for example. And knowing this is an odd function, automatically you can say it's equal to 0. I'll prove it. You can do the calculation, and we're supposed to get 0 too, as you know the term says. If you calculate it, you guys will get, you get x to the power 4 over 4, and at -2, and at 2. So at 2 is going to be here 4 to the power 2 going to be 16 over 4, which is 2, and which is 4, and it's going to be -2 to the power 4 going to be also 16 over 4, and you guys get 0 as a result. It means you can just directly say it is 0 without doing the calculations. Okay, you have just to mention your function is an odd function. That's why the integral going to be 0. Any question? Okay, I'm going to give you this one now. You guys can tell me. What is it? Which one do we have? Do we have the first situation here, the first case, or the second one?
The first.
Is sign on even or odd function?
Sir, it is the second case.
Exactly. Sine is an odd function, because you guys know sine of -x is equal to minus sine x. So automatically you can say this is equal to 0. Okay, if you do the calculation, you will get 0 too, because if you do the calculation, you guys will get minus cosine as the antiderivative, and you take it at pi by 4 and at negative pi by 4. And at pi by 4, you get minus cosine pi by 4 minus, and at negative pi by 4, you get minus cosine negative pi by 4. And this is going to be minus cosine pi by 4. And if you drop the bracket, you guys can see minus is going to be plus. But cosine is an even function. Cosine of minus pi by 4 is same as cosine of pi by 4. It's the same thing. And you see, you get 0. Exactly what we got without doing the calculation. Excuse me. Sorry. Any question? All right. If there is no question, we're gonna go to the next result. Call, the second FTC. Oops. Move this. All right, so next is, so we're done with this. You guys can keep in mind exactly what I mentioned here in this term, and we've seen, some examples. So next result is what we call the second FTC. And the second FTC here is used to differentiate a function which is defined by an integral. You guys can see capital F is a function and it's defined by an integral. Okay, the meaning of such function is, let's say you guys have this situation here. You can get, for example, so let's say you guys have capital F of X is equal to integral from 2 to X of, let's say, ln of t. Okay, so this is a function because you can calculate, the values taken by the function. Let's say you guys calculate f at 0. If you want to calculate the value taken by f at 0, so this is equal to integral from 2, you substitute x by 0, because anytime you guys have a function and want to calculate a value taken by the function, at some point, you replace the x by that value. Exactly what I did here. And then we calculate here ln of t dt. And when you integrate such function, my bad. So sorry about that, because it's going to be more complicated. I want to use 1 over t, because we haven't seen yet, the techniques of integration. I don't want to use it because it's going to be complicated. Sorry about that. I just want to use 1 over t. My bad. To simplify my calculations. Okay, I'm going to calculate f at 1, for example, because at 0 the function is undefined. I just substitute x by 1, because at 0 this function going to be undefined, because the function is ln of t, and ln of t is defined is undefined at 0. So we take it at 2 and at 1, and when you calculate it, you guys get ln of 1 minus ln of 2, and we know ln of 1 equal to 0, and it's going to be just ln of 2. You see, this is a function, and you can calculate, the value taken by the function. And keep in mind, this function is only defined when x is greater than 0. If you take an x less than 0 equal to 0, I'm just going to take the absolute value. Is going to be defined for, yeah. It's defined for all x except for x equal to 0, because for x equal to 0, the log function is going to be undefined. But for negative value, it's going to be defined because of the absolute value. And if I calculate f at 2, what's going to be the value of f at 2? Is going to be integral from 2 to 2. This is my equation. I just substitute x by 2. And what is this value? Equal to 0, because we've seen yesterday, when you integrate from a to a, you guys will get 0 regardless, the value of the function. So I'm just going to show you the form that the property that we've seen yesterday. I just use this one. When you integrate from a to a, your integral going to be 0. And that's what I use here. In my example, I'm integrating here from negative from 2 to 2. Because in this equation, to calculate the value, I just substitute here x by 2. That's why my integral becomes from 2 to 2, and I'll get 0 here. So you guys can see, you can calculate any the value of any number. Now the question is how to differentiate such function. For this function, the theorem says the derivative of f at x is only equal to the function that you guys have inside here, inside the integral. This function is your f of t, is exactly this one. And you see, the formula says calculating such integral, you have to take the same function that you have inside the integral, and you replace the t by x, because the t is the variable of integration and x is a variable for x. That's why you have to express your derivative in terms of x. Basically, it means for our example, f of t is 1 over t, and 1 over t is a derivative of capital F, and 1 over t is going to be just 1 over x. You replace your t by x, and you get your derivative. Is it okay? So quite easy to see exactly, how to get the derivative of a function which is defined by an integral. You have to take the integrand, and integrand is the function inside the integral, and then you substitute your variable of integration by x. Any question?
So, in example, at the 4 line is at minus length 2.
Pardon?
At the 4 line of example is at minus length 2. The result is minus length 2 or length 2.
Yeah, minus. Yeah, you're right. Okay, the minus sign is missing here. Length of 1 is 0 minus length 2. You have minus.
And the second line is dt or ds. 1 over.
Pardon?
The second line 1 over t dt or ds. You
Which
write
second line? This one?
for the example.
Yeah, here?
Yeah.
Yeah.
1 over t dx or dt.
Or dt, yeah. So it's dt. That's what I wrote here. It's a dt. It's just a typo. All right, thank you. Is it okay?
Yeah, okay.
All right. So let's see some example where we're going to apply exactly what the second FTC says. All right, first example, we want to differentiate this function. We've all seen this notation. D over dx means the derivative of all this integral with respect to x, because this integral is defined with respect to x. It depends on x. All right, so let's see how to do it. It's this one. So what is it? Yeah. Yes, I have it here. Yeah, see it here. All right. So this is a question, what the question says, and at the beginning, I'm going to call it capital F, and we integrate from 1 to x. And keep in mind, this is going to be my f of t. So back to our formulas here, what the term says. You guys can see we have f of x equal to integral from a number a to x, and we would like to differentiate it. And the term says you need only to take this function inside the integral, and you substitute the t by x in order to get the derivative of capital F. So in our example now, the f of t is exactly equal to t sine square t. And the term says calculating this integral is equal to calculating f dash, okay, based on what I call f at the beginning. And the theorem says you have to take this function inside my f of t, and you substitute the t by x. Doing so, you guys will get here x sine square x. You just substitute going to be x sine square x. And this is the derivative of all this function. This function is a function defined by an integral. And when you differentiate it, you take the inner function here, and you substitute x t by x. Is it okay? Now for the second example, so now we have to differentiate this integral, this function defined by an integral, but here you guys can see we integrate from x to 3x squared. It means we don't have exactly this form, because for this form, the bottom should be a constant, and we don't have it, and the top should be only x, but we have, 3x squared, which is a function. And how to do it, we're gonna, introduce a number between x and 3x squared. You can introduce any number. At the end of the day, you guys will get the same solution. I decided here to introduce 1, but you can introduce any number, 2, 5, whatever you want. As soon as you know this function is defined at that point, that's fine. So this function we know is defined because the denominator cannot be 0. It means it's defined for all real numbers. It's going to be continuous, so we can use any number. I use 1, but you can use 2 or something else. And what I did here is integrating from from x to 3x squared. I'm split it into 2 integrals. I integrate from x to 1 plus the integral from 1 to 3x squared. And we've seen yesterday this property, integrating from a to b. You can write it as integral from a to c plus integral from c to b. Okay, so back to what we did yesterday. I can show you here the properties.
Excuse me, sir.
Yeah, give me a second. I'm just applying these properties here. Integral from a to c plus integral from c to b. And it's same as integral from a to b. I just introduce a c, and in my case, the c equal to 1. Yeah, go ahead.
Sir, for question number 2 in the second step, where did the minus come from?
Minus what?
Like the minus.
No, I'm here. We'll see that one after.
Okay.
Okay. Yeah, I'm here. That's the beginning. So here I just use the property here, integral from A to B. So we've seen it's equal to integral from A to C plus integral from C to B. Okay, and I introduce 1, you can introduce 2 or any other number, as soon as your function is continuous at that point. And the reason why I introduce a number is in order to be able to use what the term says, the bottom here should be a number. Back to our second FTC, you guys can see here what the second FTC says. The bottom is A, where A is a constant. That's why I want to get A, since in my example, I don't have A here at the bottom. Okay, I'm trying to get a constant. I introduce 1. Now, second step, to answer to your question, I use another property that we've seen yesterday, because I'm trying to get the bottom as a constant. As you can see here, I told you the bottom should be a constant. And to your mic, please. And to get the constant down, I have to switch the 2 bounds. And I switch the 2 bounds, you have to multiply by -1. That's what I told you yesterday. And we've seen, you guys can see the property that we've seen yesterday. What is it again? This one, number 4. When you integrate from A to B, and you decide for some reason to switch A and B, now A was in the top at the beginning, now A is at the bottom. So you have to multiply by -1, because integrating from B to A means you going from B to A. Cannot be as integrating from A to B, which is the reverse way, the reverse direction. So that's why we have to multiply with -1 in order to stay in the same direction. Okay? And that's exactly what I use in this case. At the beginning, it was integral from X to 1, and I switch. It becomes integral from 1 to X. It means I take the opposite direction, and I have to multiply with -1 in order to stay in the same direction. Okay? Now, the second integral, I didn't change anything because the bottom is already a constant. The reason why I switch here is to bring down a constant here in order to use exactly what the theorem says. Now, we're ready to differentiate. So for the first one, we have integral from 1 to X. So use exactly what the term says. The term says you have to replace this T by X, and you will get your derivative. And that's exactly what I did here. So my f of T now becomes f of X, and with the negative sign at the front. I just copy the negative sign and apply what the theorem says. You replace your T by X, and you will get this term. But for the second term, it's a little bit different because I don't have X here. I have a function. So it means my function depends on X, and this function depends on X squared. It means it's like a composite function. And for a composite function, you guys have to use the chain rule. And for chain rule, I'm gonna apply first what the theorem says, the second FTC. What I apply here, I'm gonna apply it again. In this case, you substitute your T by 3x squared. That's what I did. In the first part, I just substitute by X because it was X. So here, I'm gonna substitute by 3x squared up and down the T here. But I have to add the derivative of this because I have a function. And the chain rule says you have always to differentiate with respect to the
Excuse me, sir.
Yeah.
Sir, I still didn't get the second step of yours.
So here,
Yes, sir.
for this negative sign,
Yes, sir.
I switch these 2 values. The integral is going from X to 1. Now it's going from 1 to
Oh,
X.
I get it. Oh, I didn't notice that.
Yeah, so that's why I said I switch. And when you switch, we saw the property. Integral from X to 1 means you consider this integral. you're going from, oops, you're going this way, let's say from X to 1. Oh, ma'am.
Yes,
Oh,
sir.
ma'am, your mic.
Oh, sorry, sir.
So you're going from X to 1. But when you switch, it's not same as going from 1 to X. Now, if you want to stay in the same direction, you have to multiply with -1 in order to change the direction and stay in the same one. Okay? And we've seen the property yesterday. Integral from B to A is equal to minus integral from A to B.
Sir, in this kind of maths, like we are not integrating the function inside. What I'm saying is you're simply inputting the integral values in the place of t's.
No, because I didn't calculate the integral. What I did is calculate the derivative of the integral.
Okay.
It's the f dash.
Okay.
Okay.
Yeah.
Okay, let me just finish this and I'll show you the proof why it's like that. All right, so here, since I have a function depending on another function 3x squared, that's why I have to differentiate the 3x squared and copy the first term. So the second term here, the derivative here gonna be 6x. Okay, so I'll let you write down this first and then I'm gonna go back to the theorems and I'll show you something. I'll let you write down the solution first. Are you done?
No.
Okay. Are you done? Not yet? So you guys are done?
Yes, sir.
Okay. Just want to give you something and you guys can see exactly the meaning of the second FTC. All right. The meaning of the FTC is, I'm just going to show you here. I'm going to pick one example. Okay. Let's say this is your function f of x, capital F. And let's suppose here is equal to integral from 2 to x. And you have 1 over t dt. And now the question is to find the derivative. That's what we wanna get, the derivative of capital F. And since my capital F is defined by an integral, okay? According to what the second FTC says, calculating such integral, such derivative is exactly equal to taking this function and replace the t by x. I'm going to show you why. We know here f of x, if you calculate it, so you guys will get here ln of absolute value of t, right? By the first FTC that we've seen yesterday. And you take it at 2 and at x. I'm just calculating this. Before calculating the derivative, I'm gonna calculate this part first. When I get it, now I can differentiate it. Is it okay? Now I'm gonna calculate it first and get ln of absolute value of x minus ln of 2. In fact, the function that I got at the beginning as a function defined by an integral is exactly equal to ln of absolute value of x minus ln of 2. Now we're ready to differentiate it. So when you differentiate it now, what's going to be the derivative? You differentiate it. You have to differentiate this, the first term. But the derivative of ln of x is equal to 1 over x, right? Minus, what is the derivative of ln of, what is the derivative of ln of 2? It's going to be 0. And then you get here 1 over x. Okay? You see, this is a long way to get the answer. But the theorem says you don't need to use a long way here because you can just get it exactly. If I use, for example, instead of calculating the function first after differentiating, based on what the term says you have just to take this function inside 1 over t. You have 1 over t inside the integral, and you replace the t by x. That's what the term says. You guys can see, and in one step, you get the solution. And this one, take more steps. You getting me now? Okay. So we with the theorem, we don't need to find first f after we calculate the derivative. In one step, you guys can get it. Now, think about, if this function is complicated, you will get more than, these 2 steps.
Excuse me, sir.
Yeah.
Sir, can you explain it once more, please?
Okay. I have a function which is defined by an integral. And the question is how to calculate the derivative of such function. That's why I use here the question mark. And I said we have 2 ways to get the derivative. And the fastest way is what the theorem tells us. The theorem says if you want to calculate the derivative of such function, you have not to go far from, what you guys have here. It's just sufficient to take 1 over t, which is inside your function, your integral, and you replace your t by x, and you will get your derivative of capital F. Here, to get this step, I only apply what the theorem says. You guys can see the term f of x is defined by this integral. You want to get f dash. What is f dash? The term says you take this function inside, which is the small f, where the t is replaced by x because my function initially depends on x. its derivative should be expressed in terms of x. Now I prove it to show you what the theorem says is right. That's why I show you the long way to get the derivative. To get the derivative, I first calculate explicitly my function. When I calculate it by using the FTC, the antiderivative of 1 over t is equal to ln of t. You take it at 2 and at x, you will get this line. Now, as I told you at the beginning, my question is to get the derivative. Now I have to differentiate this part if I want to get f dash. If I differentiate it, you differentiate the first term, you will get 1 over x. You differentiate the second term, is going to be 0. And you can notice now, using this calculation, going to give me 1 over x. And I get the same solution without doing any calculation. I just apply exactly what the term told me. That's it. Is it okay?
Sir, what if the question holds like 5 to 6 marks? In that case, also we can directly use
Exactly,
the
yeah.
formula shown in the theorem.
Yeah,
Okay, thank you, sir.
yeah. So you apply exactly what the theorem says. What? Which question? No, he just said if this was 5 marks, you have just to write the answer. I said yes.
So can you come back to the example before?
Pardon?
Can you come back to the example
To what?
example before?
Which example? The example that I did before
Yes, yes,
this?
yes.
Yeah, so you have it here.
The second example.
For the second one,
I mean the solution. Sir.
yeah, so I'm gonna, so we'll see it after. I'm just want to make sure if you guys know exactly the purpose of doing this. You have a function, and the definition of this function is complicated because it's defined by an integral. And you would like to know how to differentiate these kind of function. And the theorem told us, in fact, it's not really complicated because calculating this derivative is similar to calculating the integral first, and you differentiate. So it means it kind of back and forth. You integrate something after you differentiate it, so you will get just, the initial function. And that's what I did here. From this step, I integrated, and when I did it, I differentiate. Now I'll get 1 over x. But I save time if I already know what the theorem says. The theorem says you don't have to do all this. You're going to be just wasting time. You need only to take this function inside and you substitute t by x if it is x. But if it's not x, you replace it by the function that you have here and times its derivative. So if, for example, my function was like that, f of x equal to the integral from a to g of x. In this case, it becomes a composite of 2 functions because in this case, f depends on g and g depends on x. That's why you have to use the chain rule, and you have f of t dt. It's similar to what we have here. It's similar to this one, except the top here is not x, it's a function. And if you differentiate it, so since f depend on g and g itself depend on x, so it means you have a composite of two functions. And based on what you did in 1500, when anytime you guys have the composite of two functions, you have to use chain rule. So it means the derivative here gonna be equal to the derivative of the integral. You use exactly what the theorem says here, is gonna be f at gx times g dash. And that's what I apply in the case of the second example. Just wanna. Okay. In my second example, g of x was equal to 3x squared. That's why we multiply at the end by the derivative of 3x squared and got 6x. So I just apply the general formula in this case. So back to our now, back to here. What is it again? Yeah. In this example, you have to integrate from x to 3x squared. And I said, based on what the term says, the bottom should be a constant. And I don't have a constant because it's x and x is changing. It's a variable. That's why I introduce 1 between the x and the 3x squared. We're going from x to 3x squared. So I split it in two parts, going from x to 1. And from 1, I go to 3x squared. That's why I have two integrals. You integrate from x to 1. After that, you integrate from 1 to 3x squared. Now, for the second integral, the bottom is now a constant. So we're lucky. For this one, I still have x. That's why we need to switch in order to bring down this exponent. Bring down, the top. And as I told you, when you switch these two limits or these two bounds, you have to multiply it by -1 in order to stay in the same direction. Now, both integrals start at 1. A constant, it means we're ready to apply what the formula says. And the formula says calculating the derivative of the sum. It's not f, because this is, your function capital F, and you want to get its derivative now. And based on what the second FTC says, you take this integrand when you substitute t by x, and you will get the first derivative, the derivative of the first part. And for the derivative of the second part, this is a composite of two functions. You have to apply the general formula that I gave you here. My g of x in this case is equal to 3x squared. That's why you have to multiply by its derivative. And when you apply it, just keep in mind here, you take this function inside where you substitute your t by gx to get the first part here, or the first factor. That's what exactly I did here. I take this function and substitute t by 3x squared exactly to get this, and times the derivative of gx as the formula mentioned. And I copy the first term. The second term, the denominator becomes just 9x to the power 4 because of this square. And this derivative is equal to 6x, and you're done. Is it okay?
Yes, sir.
Thank you. Can I move to the next slide? So you all good, guys, with the solution?
Yes, sir.
All right, thank you. Oops. Okay. Now, so we're done with these 2 examples. So in those examples, we want to get the limit of this function when x is approaching to 2. And to calculate such limit, you guys can see here, this is equal to the limit when x goes to 2. And the denominator is going to 2 minus 2. The numerator, so the numerator is going to integral from 4. Now, when you substitute here, this x by 2 is going to be 2 to the power 2, you will get 4. And the integrand is equal to 2 to the power t over 1 plus t you square it. In this case, what's going to be the value of the numerator? What is this value? The
0.
numerator. Pardon?
0.
Exactly. Thank you. It's going to be 0 because you integrate from 4 to 4. And yesterday we've seen when you guys integrate from a to a, you will get 0. Denominator is exactly equal to 0. Okay? And now you guys can see, since you have 0 over 0, you can use the chain rule. You can use the L'Hopital's rule. And that's exactly what I did here. Okay? Since now we've seen how the 0 over 0 was obtained. Now, when you use L'Hopital's rule, you have to differentiate the numerator and the denominator. But the denominator is quite easy to differentiate. You guys can see x minus 2. You differentiate x going to be 1 and you differentiate 2 going to be 0. So you get just 1. And now you have to differentiate the numerator. And to differentiate the numerator, you guys have to use what the second FTC says. The second FTC says the derivative of a function defined by an integral is exactly equal to taking the integrand here inside and you substitute t by x squared. That's what I did here. When I substitute t by take x squared, I get 2 to the power x squared. And down here, I'll get x squared. You square it, it becomes x to the power 4 times the derivative of 2x. I just use what I mentioned before right here. That's what I use. I'm integrating from a to g of x. In my case, g of x here is equal to x squared. That's why I have to multiply with the derivative of x squared. That's what I did. And we'll get exactly 2x. And now when we let x approaching to 2, here going to be 2 to the power 4, which is equal to 16. This is going to be 2 to the power 4, going to be 16 plus 1, you get 17. This is going to be 2 times 2, going to be 4. The bottom is 1, that's why I didn't write it. So this 4 is coming this part. And finally, we'll get 64 by 17 as the limit of this function when x is approaching to 2. Any question? Any question? All right. Let's move on. Or you guys are
Could you
still,
please,
pardon?
could you please go to the beginning of it, like the slide before this one?
Okay, are you done with this one?
Yeah.
Everybody has done? All right.
Yes, sir.
Are you talking about this one?
No, like the way you started this example.
Or the PowerPoint?
Yeah, the power.
It's right here.
All right, thank you.
Welcome. Are you done with this? Or are you still taking the question?
Done, sir.
All right, thank you. All right, so next we will see the first method or the first technique to calculate a definite integral. As I told you, in this chapter, we will see one of the techniques, and we have another chapter dedicated to the techniques of integrations. Next week, we will cover the applications or some of the applications of definite integral. And when we finish that chapter, we will be interested in doing the techniques of integration. So here is one of the techniques, and it's called the substitution rule. And it's used to calculate, more complex integral. And when you guys wanna use this method, you're supposed to get a composite function like f at gx. You guys have seen in 1500 the composite function f at gx or f o gx, because when you guys have a composite function, your inner function going to be always your substitution, the function that you have to substitute. Okay, assuming g and g dash continuous, same for f, so it means all of them are different, are integrable. If you, for example, you guys want to calculate this integral, we're going to use the substitution rule. And the reason why we're using substitution rule is to simplify our integral in order to be able to calculate it. So here looks complicated. You start by setting your inner function is g. You call it u now. And u gonna be the variable of the new integral. Your variable of integration initially is x, and then you introduce u in order to get a new integral in terms of u. Now, by setting u, you set first u equal to g of x. Okay, I'm just going to show you how this part was obtained. You set u equal to g of x. And from here, you guys can calculate the derivative of u with respect to x. So it means you differentiate the left-hand side of what you set at the beginning to get du over dx. But when you differentiate the left-hand side, at the same time, you need to differentiate, or you have to differentiate the right-hand side, is going to be g dash. And from here, you guys can get du. So from here, you isolate your du, and your du going to be g dash of x times dx. Oops. Okay. Now, knowing du because by using this substitution, it means I'm integrating now with respect to u, not with respect to x. And if I'm integrating with respect to u, in my integral, I'm supposed to get du instead of dx. So that's why I need to calculate du first in order to substitute. And since I use my substitution, I need to find the new interval of integration, because at the beginning, my function, my integral was performed from in this interval AB, and AB is the interval for the values of x. Since I'm integrating with respect to u, I have to find the interval of u. So quite easy to find it. So you said, for example, if x is equal to a, because a is, here the first value. If x is equal to a, what gonna be the value of u? U gonna be, just from here, you substitute, x by a, and your u gonna be g of a. And this is gonna be the first value or the first limit for your integral. Now, if x is equal to b, u gonna be, so in this case, u gonna be g of b. And now we're ready to substitute. So you guys have always to find the new interval of integration. Now you guys can see here, I substitute all this by u because of what I said, and it becomes only f of u. And all this g dash times dx is your du based on what you guys have here. And this is obtained from here. And now your integral becomes only f of u, and all this is your du, and your new interval going to be from g of a to g of b, and your integral becomes easier to calculate. And this is, what we mean by the substitution rule. And when we use it, we're supposed to get an easy integral to calculate. Any question? Just keep in mind how to decide which function is u is going to be always your inner function, because you have the composite of two functions. And in a case of composite for two functions, you guys have an inner function and outer function. And your inner function g going to be always your u. Okay? Any question? All right, let's see now how to use it to solve some integrals. Oops, I'm gonna erase this. Can I? All right. So for the first integral here, we have integral from 0 to 4, square root of 3x plus 1. So in this case, what's gonna be your u? Exactly, because it's your inner function. The square root is of outer function is your f, and your g of x is 3x plus 1. Okay, because this is your g of x. And du, what's gonna be du? Because you have always to calculate du. Pardon?
3.
What's gonna be your du?
3.
No, it's not 3. It's a 3. It's a 3 times
du
dx.
dx.
Okay, just keep in mind the formula was u equal to g of x, because you guys have to show your work. Don't forget it. You need to show, you have to show us, what is your u, how to calculate your du, and how to find the new interval of integration. Otherwise, you will not get full mark. So du, as I told you, is equal to g dash times dx. Don't forget the dx. And in my case, this is u. This is gu. And that's why when you calculate its derivative, as your friend said, you will get 3, but don't forget the dx. And this is your g dash of x. Is it okay? So next step gonna be finding, you know, the new interval of integration. So interval for u. So we haven't seen yet. We have to substitute. I'm not done. All right. Here it is. Oops. No, this is the last one. Okay. All right. Okay, as your friend said, you set u equal to d 3x plus 1, and as I told you, your du going to be the derivative of 3x plus 1 times the dx. Derivative of 3x plus 1 is 3. You multiply with dx. Next step, you have to find the interval of u. And for the interval of u, as I told you before, you said, okay, if x here is equal to 0, what's going to be my u? When x equal to 0, when x equal to 0, you substitute here x by 0. And when x equal to 0, your u gonna be 1. And when x equal to 4, the second endpoint of the interval, you replace the x by 4, your u gonna be 3 times 4 plus 1, gonna be 13. So it means we're gonna integrate from 1 to 13. And you guys can see now, integral from 0 to 4 becomes integral from 0 to 13. Under the square root, this is what we call u at the beginning. We just replace by its value. And now we have to get dx. But dx, you guys can get it from here. Okay? So from here, you guys can see dx, because you need to know dx and substitute by its value. So dx is going to be du over 3. And that's what I did here. And this is going to give me all this. This is my dx. Is it okay? And the u under the square root is just, you know, the 3x plus 1. And I substitute my dx by its value, which is equal to 1 by 3 du. Okay? So next step, I took here 1 over 3 out of the integral because it's a constant. You can do it. You have the right to do it anytime you have a constant inside. We've seen, you know, the property yesterday. So when you take it out of the integral and the square root of u, you guys can write it as a power function. It's going to be u to the power half, because under this form, it's going to be easier to calculate, you know, the antiderivative. And now for the antiderivative here, you will get u to the power 3 by 2 times 2 by 3. So you take it at 1 and 13. Now at 13, so I just first took here the 2 by 3 out of the bracket to multiply with 1 over 3. It becomes 2 by 9. And when I substitute, you know, this u by 13, I'll get 13 to the power 3 by 2. And when I substitute by 1, it becomes only 1 to the power 3 by 2 equal to 1. But 13 to the power 3 by 2 is equal to 13 root 13. Okay, so you guys can see it here. 13 to the power 3 by 2 is exactly equal to 13 to the power half to the power 3. And this is equal to root of 13 to the power 3. And root of 13 to the power 3 is equal to 13 root of 13. You square it times root of 13. And this is equal to 13 root of times root of 13, as I told you. So it means I just substitute here and I multiplied by 2. That's why I got here 26 root 13. The 2 I multiply by 1 to get negative 2, and the whole thing to the over 9. And you're done. Any question?
Sir, it is necessary to do the last step, or can we leave like that only?
Pardon?
It is necessary to do the last step, or can we leave it like that only?
Yeah, it depends. If the question asks you to simplify as much as possible, you have to write it like that. Otherwise, you can leave it like that. Any other question?
Hello, Professor.
Yeah.
So I'm using my mobile, so I'm just changing my to this laptop because my battery is low. So can you allow me to in?
Yeah, I already
Okay, it's came. Okay.
accepted. Yeah.
Thank you.
Well, any question? All right, so let's see the second example. All right, in the second example, I'm gonna erase this. All right, example number 2. We're gonna set u equal to exactly. So we're gonna set here u equal to 3 minus 5x is your inner function. And in this case, your du gonna be
Minus 5dx.
exactly gonna be, you differentiate this part. This is your gx. So when you differentiate it, it's gonna be minus 5, and you multiply with or by dx. And then from here, your next step gonna be finding the interval for u. And you guys can see if this is 1, the first endpoint for x, and this is the second endpoint. So you have to substitute here in order to find the new interval. So when x equal to 1, your u gonna be 3 minus 5 gonna be negative 2. And when x equal to 2, u gonna be 3 minus 10 gonna be negative 7. So it means we're gonna integrate from negative 2 to negative 7 with respect to u. Now let's see the solution. All right. As I said, we set u equal to 3 minus 5x, and your friend told us you're going minus 5 dx, or you do u, and you find the new interval if x is taking the values between 1 and 2. At the same time, u is taking the values from -2 to 7, to -7. And as I told you how to do it, you substitute here x by 1, and you will get 3 minus 5, going to be -2. Second endpoint, you substitute x by 2. You substitute here is going to be 2 times 5, going to be 10. It's going to be 3 minus 10, and we got here -7. Now the integral becomes integral from 1 to 2, going to be integral from -2 to -7. And here is the denominator you substitute, by u based on what he said is going to be just 1 over u squared. And the dx, you guys can get it from here. Okay, so let's see. So from here, you guys can see dx. Dx is equal to, because we need to know dx in order to replace or substitute by its value. So dx is going to be du over -5. And that's what I use here. It's my dx. Okay, I just substitute here dx by its value. And I got here 1 over u squared, and I substitute dx by its value. Now, -1 over 5 is a constant. We can take it out of the integral. It becomes a -1 over 5. And we're going to integrate here from -2 to -7. And the 1 over u, I'm going to write it as a power function. You send it to the top. It becomes a u to the power -2, as you know. And you still have your du, means you integrate respect to u. Now, calculating this, the antiderivative. So you guys get -1 over u. Take it from -2 to -7. And at -7, you already have minus, and this minus becomes 1 over 7. And we have -1 over 2. And after calculation, you guys get here 1 over 14. Any question?
No, I don't. I'm okay.
Sir, when we use du,
Pardon?
when we use du instead of ds.
I didn't get you.
Uh,
The du is here.
no, I mean, why we not just show it like ds at the way the reverse way, but we change from ds to du.
Because you change your variable of integration. You integrate respect to u, cannot be dx. Dx is when you integrate respect to x. It should be always du. Your new variable is u, not x. The du means this integral is calculating with respect to the variable u. That's why we have to use du instead of dx, because you use a substitution. You see here, this is the third time we apply it. Is it your question or is something else?
Oh, okay.
Is it okay?
Okay, thank you.
It's exactly to same as what we did before. If you have to integrate respect to t, you will get dt. If your integral is with respect to x, you get dx. With respect to z, you're going to be dz. With respect to y, you're going to be dy. Any question?
Someone on the chat is asking how you got u square. His mic is not working.
Or how to get this? Or how to get this? U square here. Mahmoud? Okay, I cannot read at the same time what you read. Okay, how I got u square?
Yes. Yep.
Because this is your u. You see at the beginning?
And yep, got it.
Okay, I did it here. You see at the beginning? This is your function and your u.
Yeah, got it.
You have here 3 minus 5x as your u. So your u is going to be just u square. Based on what we said here. Is it okay?
Yeah, he said he got it.
Pardon?
He said he got it. It's okay.
Okay. So you guys can see this is your u and your function here is at the bottom is 3 minus 5x u squared. So if you substitute this by u, it becomes a u squared. That's what I did here. Only this part is u. The square is not part of the u. The u is only what you guys have inside the bracket. That's what we said, because I told you your u going to be always the inner function, and the inner function is just the bracket here. And when you replace it, it becomes a u square. Is it okay?
Yes.
Any other question? Okay. All right. So next now we're done with the definite integral. Now I'm gonna do the third part dedicated to the indefinite integral. And I'm going to start by talking about, the antiderivative function that you guys have already seen in 1500. And just keep in mind here saying capital F is an antiderivative of this small f means when you differentiate capital F, you will get the small f. Okay. And here is one example. If my small f is x squared, an antiderivative of x squared is equal to 1 by 3x cubed, because you guys can see when you differentiate this function, you will get x squared. As you can see here, if I calculate the derivative of capital F, I will get the small f, which is equal to x squared in this case. When you differentiate capital F, you guys will get x squared. And this is exactly what the definition says. Okay, so it means capital F equal to 1 by 3x cubed is an antiderivative of x squared. And that's exactly what we use when we're calculating, definite integral. And just one remark here. Again, we realize g of x and h of x are both, antiderivative too, because they satisfy exactly what the definition says. When you differentiate g, you will get f, the small f. You guys can see when you differentiate g, is gonna be, you differentiate the first term, you get exactly x squared, and the second term gonna be 0 because this is a constant. Same if you differentiate, oops. Same when you differentiate h. So the derivative of h is gonna be x squared too, because when you differentiate, you guys will get, you differentiate this part is going to be x squared. And this part going to be 0 too, because it's a constant. What we can draw from here is the antiderivative function is not a unique function, because for this example, we found 3 antiderivative functions, and they have a common term, which is equal to 1 by 3x cubed, and the difference is just the constant. You guys can see here for the first case, the constant is 0, it's just plus 0. For the second one, the constant is 3, and here's -4. So basically, it means to find an antiderivative, you take just the common the common term, and you add any constant. It could be 3, -24, 0, 7, root of 4, root of 7, and so on. Okay? And we would like to find now the general formula for all of them, because we realize we have a many or infinite many antiderivative function. And to represent the antiderivative function, knowing they have a common term, we just copy the common term, and instead of the constant, we don't have to specify it. And what I call the most general antiderivative, I'm going to call it, for example, capital M for this example. This is the most general antiderivative. It means the family of functions satisfying what the definition says, all of them. And all of them will be given by 1 by 3 x cubed, which is, the common term, and plus a constant c, when c is an arbitrary constant, could be any number. C could be 0, 5, 3, -24, and so on. And this is what we mean by the most general antiderivative, as you've seen, in 1500. And it's a family function, because as soon as you fix the value of c, you get one antiderivative function. When c equal to 0, you guys will get this case. When c equal to 3, you will get g. When c equal to -24, you will get h. And when c equal to root of 7, you get another antiderivative function. Okay? So that's why when you guys want to get the antiderivative functions, sorry. So when you guys want to get the antiderivative function, you have always to add the constant c, because without the constant c, you only provide one antiderivative function among all of them. That's why when you don't add the constant c, so you will not get full mark, because you didn't, in this case, you will not answer entirely to the question. And that's what I mentioned. Yeah. Hello? What did you say? Hello?
So
Okay.
I accidentally opened my camera, so sorry. I mean, voice.
Okay, so if capital F is an antiderivative of the small f, the most general antiderivative, as I said, is a family of functions given by an antiderivative plus a constant c. And we don't have to specify it, because as soon as you specify a value for c, you will get just one of the antiderivative. And the most general means, all of them. Okay? And second definition here is, in fact, what we call most general antiderivative is exactly what we mean by indefinite integral. And it's denoted by the long s as what we did for integral, except here we don't have the interval a, b, because we have a function. If you have a definite integral from a to b, you're supposed to get a number. So here, indefinite integral, you're supposed to get a family of functions. Be careful. You see the difference between the two kinds of integrals. For the definite integral that we did so far, when you calculate it, you get a number. But for indefinite integral, you get a family of functions f of x plus c. Okay. Basically, it means the most general antiderivatives you guys have seen in 1500 is exactly what we call indefinite integral, and the notation is as long as the what we did for definite integral, except here there is no endpoint because we calculate a family of functions. If you add the endpoint, you will get a number. And before doing some examples, just want to remind you, this formula that we've seen, it is just a power rule for the integral. If f is equal to x to the power n, its antiderivative going to be x to the power n plus 1 over n plus. We use it, today many times, this formula, because it's an easy example. And you can apply it, no matter what is n, except when n equal to minus 1. Because when n equal to minus 1, x to the power minus 1 is exactly equal to 1 over x. And 1 over x is the derivative of ln of absolute value of x. That's why. Okay? Otherwise, you can always apply the first formula for n positive, negative, equal to fraction. So you can always apply it. And that's what we did in the previous many of the previous examples. The power rule for integral, it's different to the power rule for derivative. Is the reverse of the power rule of derivative. For the derivative, x to the power n has its derivative equal to n times x to the power minus 1. So here we take the reverse away. So that's why it's going to be n plus 1 over n plus 1. Is it okay? All right. All right, first example here. All right, for this one, integral of cosine of x. All right. So you guys will get, what is the antiderivative of cosine? So you get, thank you. You guys will get sine of x plus c, exactly. Don't forget the c. If you only use sine x, you get one antiderivative. And for the second example, this is equal to integral of x to the power negative 2. And when you use the power rule, I'm talking about this rule. Now we're going to use it when n equal to minus 2. So it means you have to use this part. N equal to minus 2, not equal to negative 2, 1. So when you use it, it's going to be x to the power minus 2 plus 1 is going to be negative 1 over negative 1 plus c. And again, this is equal to minus 1 over x. And you're done. Is it okay? Right. And the third case, so the third case is similar to what I said. Now x equal to minus 1. In this case, is you guys have the log function. It's going to be the natural logarithm of absolute value of x, because x is a free variable under this form, could be in positive or negative, and we don't know. So that's why we need to take the absolute value in order to make sure the log going to be defined, and plus now the constancy. Any question?
Yes, sir.
Pardon?
All good.
All good. All right. Now I'm just going to give you two properties of the indefinite integral. It's similar to the property that we've seen before. Calculating the integral of a sum is equal to the sum of integrals. So you have to integrate f and g, but when you're done, you just add one constant. Okay, there is no need to add two constants, c and d. It's going to be just one constant because c plus d still equal to a constant e. Okay, and k times f going to be the integral going to be k times integral of f, because k is a constant that with respect to x doesn't depend on x. You can take it out the integral. And we've seen, these two properties in a case of definite integral. So we just repeat the same thing. All right, so here just want to calculate this example. So this is equal to integral of 4x, 4 sine x, sorry. But this one is, the first term is quite easy to integrate, but the second term here looks complicated. That's why I need to transform it, to simplify it. And in this case, I'll get here plus 2x to the power 5 minus, but root of x is equal to x to the power half. It's going to be x to the power half over x. Okay, and then we can use now what the term, the property says. Integral of a sum equal to sum of integrals. It means we can integrate the first function, the second function, and the third function, and we're going to add one constant c. But before doing that, I'm going to simplify the second and the third term. I'll get here 4 sine x and for the second term is going to be plus 2x to the power 4. And for the last term here, x, you send it to the top, it becomes x to the power minus 1. So x to the power half times x to the power minus 1 is going to be x to the power 1 by 2 minus 1. It becomes a negative 1 by 2. Now we're going to apply what the property says. When you guys have 4 times a function, the integral going to be 4 times integral of the function. It means you can take the 4 first and you integrate sine. But the integral of sine is equal to minus cosine. You're right. And plus 2 times, for this one, we've seen going to be x. We just use the power rule for integrals. Going to be 4 plus 1, going to be 5, divided by 4 plus 1, 5. And minus, we use again the power rule. We get minus 1 by 2 plus 1 is going to be x to the power 1 by 2. Because minus 1 by 2 plus 1 is going to be 1 by 2. And we divide by n plus 1 again. When n equals negative 1 by 2, is going to be 1 by 2. And plus now the constant c. So we can simplify it now. It's going to be minus 4 cosine of x plus 2 by 5 x to the power 5. And when you divide by a fraction, you guys know, dividing by a fraction is exactly equal to multiplying with the inverse of the fraction. But the inverse of 1/2 is 2/1. So that's why 2/1 will get 2 times. And the root, the x to the power half is just equal to root x plus the constancy, and you done. Is it okay? Is there any question? All right, so we'll not have time, to solve the next example. I'm gonna leave it here until next week, and we'll do the second example, and we'll conclude this chapter. And before letting you go, I'm just gonna take the attendance because actually it's 9:49. If you guys are done with this, let me know. I'm gonna take the attendance. It's all good?
Yes, sir.
All right. So in that case, I'm gonna start sharing the all right. All right. Okay. All right. Bagambit is here. I saw you. Yeah, and Fatima.
Here, sir.
Thank you. Alamin, I saw you. Are you still here?
I'm here. Yep.
Yeah, Janky Bao.
I'm here.